3.1 on exponential equations. So an exponential function has a base of b and is in the form f of x equals a times b to the x power. X is a real number and a and b are real number constants. A cannot equal 0 and b is positive and cannot equal 1. So you have two different graphs here, one showing exponential growth and one showing exponential decay. So the numbers are either going to increase at a really fast rate or decrease at a really fast rate. And there's going to be some sort of a horizontal asymptote on all exponential functions. The a value is always going to be the initial value in the exponential function, and b is going to have to do with the rate of either increase or rate of decrease. So example 1 says to graph and describe the domain, range, intercepts, asymptotes in behavior, and where the function is increasing or decreasing. So all of these are things that we've learned in chapters 1 and 2, and we need to continue to bring those up anytime we're talking about functions to be able to describe the graph of that function. So f of x equals 4 to the x power. Here's a picture of the graph and the table. You can see from the table that the further that I go in the negative numbers, the further I go to negative infinity, those numbers are going to get smaller and smaller, and they're actually getting closer and closer to 0. You can see that in the graph as well. It looks like it touches on the x-axis or y equals 0, but it's going to get closer and closer to that axis as it goes further left. And then to the further right, the numbers are getting exponentially larger. You can see that. Okay, so first we're going to talk about the domain. Domain has to do with the possible x values. So with this exponential function, we just talked about that it's going to continue to go to the left infinitely, so that's negative infinity. And then as it's going to the right, it's actually increasing, but it's going to continue going to the right infinitely as well. So the domain is from negative infinity to positive infinity. Then the range is the y values, so from bottom to top. The lowest y value is going to be that this graph is getting closer and closer to 0. Wherever that horizontal asymptote is, that's what the graph is getting closer and closer to, and that's where the range is going to start. And then this graph is going to continue going up infinitely, so the range will be from 0 to positive infinity. Okay, next are the intercepts. So the x-intercept is where it touches the x-axis. And we've talked about that this graph is getting closer and closer to the x-axis, but it's never going to touch it, so it actually does not have an x-intercept. Then for the y-intercept, that's where x is equal to 0. And so for this function, that's going to be at 1. So 0, 1 on this graph is the y-intercept. Okay, next will be any asymptotes. There are no vertical asymptotes on this graph. You would be able to see that if there were any breaks in the graph or a hole or any errors in your table. So there's no vertical asymptote, but there is a horizontal asymptote at y equals 0, and that's whatever the graph is getting closer and closer to. You can see those values in the table, that all of the y values, the further up you go, those are getting closer and closer to 0. Okay, then for the end behavior, this one's going to be a little different from other functions that we've talked about, because as x approaches negative infinity, the function is actually approaching 0 instead of negative infinity. And then on the right-hand side, as x approaches positive infinity, the graph is still approaching positive infinity. It's going to continue to go up. And then last thing is to talk about when the function is increasing, decreasing, and or constant, and that's going from left to right. So from left to right, this function is always increasing. So from negative infinity to positive infinity, this function is increasing. Okay, next thing we're going to look at is the compounding interest formulas. So the first one is a equals p times 1 plus r over n raised to the nt power. Okay, so for everything in this formula, we have the definitions over here on the right-hand side. A equals the balance of the account. P is the principal investment or the initial investment into the account. R is the rate, always as a decimal and not as a percent. T is always represented time in years. And N is the number of times that the interest is compounded throughout that year. So they're going to tell you that it's monthly, quarterly, semi-annually, annually, and you're going to plug the number in that would be appropriate for that. Then the other compounding interest formula is for continuously compounded interest, and that is A equals P times E to the RT power. And E is the Euler number, 2.71828 continuing, and it's a number that appears a lot in financial situations for continuously compounding things. So let's use these two formulas to solve a couple problems. So example 2 says that Ms. Salzman invested $2,000 into an educational account for her daughter when she was an infant. The account has a 5% interest rate. If Mrs. Salzman does not make any other deposits or withdrawals, what will the account balance be after 18 years if the interest is compounded monthly? So we're going to use the compounded interest formula, not the continuously compounded. It would say continuous in the formula if you were supposed to use that, or in the problem. This one is compounded monthly. Okay, so let's pull out all of the information from this problem. First thing is the principal investment is $2,000. The rate is 5%, so that will be 0.05. And then the time is 18 years. Okay, they also said that it's compounded monthly, so that's going to be compounded 12 times throughout the year. So we're going to plug in all of our variables into the equation. So 2,000 times 1 plus 0.05 over 12 raised to the 12 times 18 power. You can type this in all at once if you want to. You might put parentheses around the two numbers in the exponent, but it should be pretty easy to plug in. So once you type this in, you're going to get 4,910 and 2 cents. Since this is dollars that we're talking about, you need to round to 2 decimal places. So the balance of the account at the end of the 18 years will be $4,910 and 2 cents. Okay, example 3 says that if $1,500 is invested in an online savings account earning 4% per year compounded continuously, how much will be in the account at the end of 18 years if there are no other deposits or withdrawals? So since this one says compounded continuously, we have this formula, A equals P times E to the RT. We still need to pull the information out of the problem. So our initial investment is $1,500. Our rate is 4%, or 0.04, and the time that we're going to invest it is 8 years. So we plug all of that into the formula, 15 times E raised to the 0.04 times 8 power. On your calculator, the E button is on the left-hand side, and you're going to hit second and the LN button on the left-hand side. You should be able to type this in, and you get that the balance will be $2,065.69. So the balance at the end of her 8 years will be $2,065.69. Okay, the next two formulas are very similar to the previous formulas. This is just talking about exponential growth and decay in general for all sorts of problems. We could be talking about population of people, of animals, the growth or decay of bacteria or of medication. Lots of different application can be used for these exponential functions. And they look pretty similar to the previous ones. They have different variables, but initially they mean the same thing. N sub 0 is the initial amount. R is rate, T is time, so very similar information. The only difference on this is if you're talking about growth or decay, you're going to change the sign of the rate. So if you're talking about a growth situation or a value that's increasing, you're going to be a positive rate in your equation. If it is talking about decay or something decreasing, then you're going to plug in a negative rate into that formula. So let's do a couple of examples using those. So example 4 says that a state's population is declining at a rate of 2.6% annually. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 years and then in 30 years. So this is the formula we're going to use. N equals n sub 0 times 1 plus r raised to the t power. Okay, so our initial value or our population is 11 million, and our rate, since it is declining, will be negative 0.026. Okay, then we're going to plug in 15 years and then 30 years for time. So we're going to do two separate problems, one for 15 and one for 30. Now I didn't write out plugging these numbers into the equation because it's such a short equation. So when you plug in for 15 years, you get that the population will be about 7,409,297. And then if you plug in the same information, changing the time to 30 years, the population will be about 4,990,699. Since we're talking about people and population, we don't want to round or use the decimal of any form because you can't have 0.3 or 0.5 of a person. We only want whole people. So anytime you're talking about real objects, we don't need to round up. We'll just leave the whole number as it is. Okay, last example shows the population of the growth of deer in a forest from 2000 to 2010. If the number of deer is increasing at an exponential rate, we're going to identify the rate of increase and then write an exponential equation to model this situation. So we don't know the rate of increase here. That's what we're going to solve for first, and then in the very end we'll write a general equation that could be used to find the population of deer at any time. So, since in 2010 the population had gone up to 264, we're going to start with 264. In 2000, the population was 125. So 125 is our initial value times 1 plus r, our rate, and the time that we're talking about here is 10 years. So what we need to do is solve for our rate. So since 125 is being multiplied by the parenthesis, we're going to divide by 125 on both sides first. So 264 divided by 125 is 2.112, which equals 1 plus r to the 10th power. So next I need to get rid of the 10th power. You could take the 10th root of both sides to get rid of that. That's the same as raising to the 1 over 10 power. So it's just easier to type in your calculator to raise this number to the 1 over 10 power. So type 2.112 raised to the 1/10, and you're going to get 1.0776 equals 1 plus r. And then to get the rate, we just need to subtract 1 from both sides. So our rate then is 0.0776. So this means our rate of increase is actually 7.76%. So now what they want us to do is to write an equation using this rate and the initial value, and we're just going to leave a variable in place of t. So I'm going to say that the population equals 125 times 1 plus 0.0776 raised to the x power, or you could put t power, either way.